Welcome back to BE 110. Today we'll do some examples of strain fields and flow patterns using the tools that we've derived over the last week or so. So let's consider the example of plane strain. You'll remember we did plane stress. Well, there's an analogous definition of a plane two-dimensional strain situation, and that's one in which the deformed coordinates little x1 are only functions of the original coordinates big X1 and big X2. Similarly, little x2 are only functions of big X1 and big X2, and little x3 is equal to big X3, or optionally plus a constant, which would just be a rigid body translation, three direction. And so this would result in a deformation gradient tensor FIR with components F11, F12, 0, F21, F22, 0, and then 0, 0, 1. And then using that to calculate the strain, we would get strain components ERS that were only in the first and second rows and columns, where the third row and the third column would all be 0. So that's the definition of plane strain, and you get the same pattern for the Almancy or Cauchy strain tensor definitions. This next example of pure torsion is most easily done in cylindrical polar coordinates. So imagine we have a cylindrical bar, or it could be a tube here, with constant radius and length shown here as L torque. Subject some torque or twisting moment to it with a moment arm of L twist and a force F external. And the result is that holding this end fixed, that this end would twist or rotate through theta degrees. And every plane along the length here would twist a little bit less in proportion to the distance along the length, so that the twisting angle is a constant in proportion to the length. And we'll call that constant alpha, which would be this theta divided by this L torque. And you see that that's the only thing that happens. The radius doesn't change, the length doesn't change. There's just a circumferential displacement that increases proportionately as we move along the length from z equals 0 here to z equals L torque. So calling the twist per unit length alpha and writing the displacements in polar coordinates, then the deformed radius will just equal the undeformed radius. Deformed theta will equal undeformed theta plus an increment proportional to the z coordinate times the constant alpha, and then deformed z will equal undeformed z. So to go further, we need to be able to write the deformation gradient tensor in cylindrical polar coordinates. In other words, where our deformed coordinates, instead of being little xyz, are little r theta z, and our undeformed coordinates are capital R, capital theta, capital Z. So the deformation gradient tensor would no longer just be partial derivatives, and in fact the proper definition in polar coordinates of the grad of x, where the capital G indicates partial derivatives with, or a gradient with respect to undeformed coordinates, would look like this, where the components FIR would be del little r, del big R, just as you would expect. But then instead of del little r, del theta, an element of length in the circumferential direction is r d theta, so this is 1 over big R del little r del theta, then del r del z. Then similarly, instead of being del theta del r here, it's r del theta del r, because an element of length is r d theta. Then r d little theta over big R d big theta, r d theta dz, dz dr, 1 over r dz d capital theta d little d z d big Z. So you can see the only difference here is that wherever there was a d theta, there's an r associated with it, and that's because an element of length in the circumferential direction isn't d theta, it's r d theta in polar coordinates. And so then applying this to the displacements that we've defined, then del r is 1, and del theta and z is 0. Del r is 0. Del theta is 1, but we have an r upon r here. And then del z is alpha, and there's an r here, so we get r alpha. Then del z is 1, and del r and theta is 0. So now we have the deformation gradient for this problem, and we can proceed from that to compute the components of the strain tensors and the right and left Cauchy-Green deformation tensors in the same way that we did before. This next example is more of a proof or exercise, and the exercise is to prove that if a line segment stretches by a certain stretch ratio lambda such that it is deformed from an undeformed length of delta capital L to a deformed length of delta little l, so that del little l equals lambda del big L, where del big L is the undeformed length. The problem is to show that lambda squared is equal to AR times AS del xi del xr del xi del xs, and you might recognize that latter term as C, the right Cauchy-Green deformation tensor, or in vector and tensor notation this would be A transpose C A, where A here is the unit vector in the direction of the undeformed line segment delta with length delta L. Okay, so to prove this, let's first define delta x in the deformed state, which would therefore be delta L, which is the magnitude of that element, times A, which is the unit vector, and then delta big X to be delta big L times capital A. Little a and capital A could be different because the segment could have rotated. So that would then say that delta L by little a must equal F by delta L times big A, because that's the definition of the deformation gradient tensor. Now, using the fact that the stretch ratio lambda is delta little l over delta big L, then we can rewrite this expression as lambda A equals F by A, or in index notation, lambda A sub I equals dxi del xs times AS. Next, we square both sides, which gives us lambda squared AI, or A dot A, which would therefore equal FIR times AR times FIS times AS, where FIR and FIS are del XI, del XR, and del XI, del XS. Now, AI times AI, since A is a unit vector, will be 1, so that gives us lambda squared equals AR times AS del XI, del XR, del XI, del XS, which is what we wanted, or writing this in terms of the deformation gradient tensor, that's A transpose FA, which is therefore A transpose CA, which is the result we were looking for.